Good morning. All right, so we're going to finish up one more example in section 4.1, then we'll get into 4.2 today. I did move the due dates for the early stuff in chapter 4 and also the rest of the homeworks kind of from here on out. Hopefully, we'll be able to hit those due dates, but again, those will get adjusted if we need to. But again, the goal for today is to finish up 4.1 and 4.2, and then we'll kind of see where we are at that point. Probably won't get to 4.3 until next week, though. Okay. Any questions? Oh, don't forget also that the test is due by midnight tomorrow night on chapter 3. So if you haven't taken that yet, just make sure you find some time today or tomorrow to sit down and take that test. Okay, so don't forget to get that done. Right, any questions, comments, concerns now before we get started today? All right, so compound interest, right? So this is one of our most common uses of our exponential growth in terms of real world scenarios. So we have A of t equals p times 1 plus r over n to the nt power. So notice here the n times t is in the exponent. And what each of these things represents now, our A of t is an amount of money after t years, right? So that's an accumulated amount of money after we've invested for a certain amount of time. The P in this case is principal, which is the starting amount. Okay, so this is always however much money you're starting with. All right, then our R value is going to be our interest rate per year. This needs to be converted to a decimal, right? Because normally you're going to be given a percentage for your interest rate. We always want to change that to a decimal before we actually substitute it into our formula. N is the number of times that we're compounding our interest per year. So there's going to be some keywords that we have to look for here to know what that N value is, and we're going to go through what some of those could be. And then T is always measured in years for this formula. Okay, so that's always going to be the number of years. Now let's think about our N value and what some of those keywords could be. So if we have N here, and then the keywords that we're looking for. So does anybody know any keywords that we could look for that would tell us how many times we're compounding our interest per year? Monthly, good, right? So one keyword we could look for is the word monthly. If we're compounding monthly, how many times per year would that be? 12 times per year. Good. So our N value in that case will be 12. All right, good, Destry. So annually would be another one. So if we see the word annually, how many times per year are we compounding? Just one, right? So annually means once per year. So our N value would be 1. Okay. Any other keywords that you might want to look for? Weekly is another one. Good. If we're compounding weekly, how many times per year would that be? Good. There's 52 weeks in a year. So if we compound weekly, that would be an N value of 52. Okay. Quarterly is another good one. So if we're compounding quarterly, how many times per year would that be? 4 times per year. So our N value would be 4. Any other ones that you've seen before? Okay, so biannually is one, right? And another way that you might see that is semi-annually. Those are going to mean the same thing in terms of keywords. Okay, so how many times per year would that be? Twice, right? Okay, so if you see either one of those keywords, semi-annually is the one the book uses most often. But if you see either one of those, okay, they both mean 2 times per year. Bi-weekly is another one. We're not going to use that one, so I'm not going to write it out, okay, but that would be half of the 52 in this case. And that one's used a lot. Well, not even so much. I was going to say, like in mortgage interest, you might see bi-weekly because you can make bi-weekly payments. And so that would be 26 times per year. Okay, but I think this is probably a good start here. I think these are the ones we use most often. So monthly comes up a lot, weekly, quarterly. Oh, there's one more. Um, Daily is the other one. Okay, so it is possible to do this daily also. If we were to compound daily, how many times per year would that be? 365. Good. And that's always going to be the case. We never worry about leap years. Okay. So it's never going to be 366, always 365 for daily. That's the same thing with a bank. So even your bank is going to use 365 even during a leap year to compound your interest if it's daily compounding. So just know that that's always going to be the case for daily. Okay. All right, so those are the ones we need to worry about. So let's take a look here at this example. So we have a sum of $1,000. We're investing it at an interest rate of 12% per year. We want to find the amounts in that account after 3 years, and we're going to do this annually, semi-annually, quarterly, monthly, and daily. Right? So we're going to do this 5 different times just to see what the difference is and how much money we would have. Okay, so again, our formula here, A of t equals P times 1 plus R over N to the NT. All right, so let's start here with annually. So let's pull out what we know first, right? So what does that $1,000 represent for our equation? That's the P, good. So that's the principal, that's our starting amount. So there's our P value. What about the 12%? That's our R value. And remember, we need to change that to a decimal. So what would our decimal be for the R? 0.12. Good. So R equals 0.12. Because remember, to go from a percent to a decimal, we move the decimal place 2 places to the left. So it starts after the 2. We move it 2 places to the left. That gives us 0.12. All right. And then finally, the 3 years tells us what? That's our T value. And so now, if we're compounding annually, that gives us the N value. So what are we going to use for N this time? That's 1. Good. So this tells us that our N value equals 1 for this first one. All right, so now I'm just going to substitute everything in. We're going to have A of t equals our P value is 1,000 times 1 plus our R value is 0.12 over N, which is 1. And then our exponent's going to be N times T, which is 1 times 3. Any questions about the setup for that one? Okay. Now it's up to you. If you want to go step by step through this one, you can. If you just want to put all of it in the calculator, you can do that also. Just be careful with like the 1 times 3 and the exponent. Make sure that's all grouped together up there. But if we were to do this, and I'll do the step by step real quick just so we can see it. You have 1,000. This is just going to give us 1.12 in here, right? Because 0.12 divided by 1 is 0.12. 1 times 3 is 3. And so if we put all that in the calculator now, what should we get for our accumulated value? Good, right? So this is $1,404.93. And notice here we rounded to the hundredths place because we're dealing with money, so you always want to round to the nearest cent. Okay, so always round to 2 decimal places if you're doing an accumulated value. Any questions on that one? Okay, now let's do the others. So now if I want to do semi-annually next, what's our end value going to be now? 2. Good. So now we use an end value of 2. Everything else stays the same though, right? So we haven't changed anything else. We're looking for A of t equals 1,000 times 1 plus 0.12 over 2, and then 2 times 3 as our exponent. Now, if you put all that in the calculator, the nice part about this is if you do second and then enter, if you have a TI calculator, it'll bring back up the last work that you did, and then you can just edit the 1 and make it a 2, right? So if you type in the whole thing, then it's pretty easy just to go back and just change that 1 value if you're trying to do several of these. Okay, so just kind of a shortcut there. But if we do all of that now, and again, I'm not going to do this step by step, we'll just put it in the calculator. What does that give us for the accumulated value? Good. So $1,418.52. So notice in this case, right, when we only compounded annually once per year, it was $1,404.93. Now compounding semi-annually twice per year, we've made a little more money, right? In the same amount of time, same interest rate, okay, we've made almost $14 more over those 3 years. All right, so that's that one. All right, now, if we do quarterly, we said that end value is going to be what? Good. So we use an end value of 4. Again, everything else stays the same this time. So 1,000, 1 plus 0.12 over 4, and then 4 times 3 is our exponent. So whenever you get that one, let me know what you got. All right, so 1,425 and 76 cents. Good. Any questions on these? You are not able to get those values using your calculator. Okay. All right, so in each case, right, we're asked to do this 5 different times, once for annually, then for semi-annually, then for quarterly, then for monthly, and then for daily. And so that's why we're changing the end value, because each one of those words means a different end value. And you can kind of see that each time we change that end value, right, the more times per year that we compound our interest, the more money we're making, right? It's not a significant difference necessarily, okay, but it is more depending on how many times we compound. All right, so I'm not going to do the last 2, right, because I have a feeling if you can do these 3, you can do the other ones. Again, though, real quick, what is N going to be for monthly? That's going to be 12. Good. And for daily, that's going to be what? 365. Good. Okay, but that's all that's going to change. You're still using that same formula you're plugging in. And just if you want to know what those would be, for monthly, A of t comes out as $1,430.77. And then the last one, if we do daily, we end up with $1,433.24. Okay. So if you wanted to try those on your own and just check to make sure you can do it, okay, those are the values you should get there. Any questions at all on setting these up or finding those values? All right. Let's look at 4.2 then. All right, so 4.2, the natural exponential function. All right, so in the first section, we just looked at exponential functions in general with many different bases, right? Now, our natural exponential function is a very specific exponential function where the base is e. Okay, so we have f of x equals e to the x. That's what we call the natural exponential function. E in this case is referred to as the exponential function a lot of times. So if you ever hear somebody just say the exponential function, this is the one they're referring to. Okay, E itself is the natural base, and E is a number, right? So just like pi represents a numerical value, E also represents a number. So if you notice on your calculator, you should have a key that has E on it. Normally, you'll have like an LN key. And if you press second and then that key, that'll give you E to the X. And so if you do that just to the first power, you'll see that E is approximately 2.7183 if we were to round that off to 4 decimal places. So whenever we're doing like E to the X now, remember we looked at something that was like 2 to the X. We also looked at 3 to the X. Well, now E to the X is somewhere in between those, right? So it's still exponential growth. It's still going to be a J-shaped curve when we graph it. And it's going to be somewhere in steepness between 2 to the X and 3 to the X. Any questions about E to the X now, or just E in general? And this is why normally in algebra we don't use E as a variable, right? If you're trying to solve an equation, because E normally represents an actual numerical value, and so we don't want to get that confused. Okay. All right, so now we just want to evaluate each one of these, just like we did example 1 in the previous section. We're going to use our calculator. This time it wants 5 decimal places. So again, make sure you can locate the E key on your calculator. And we're just going to do E to the 3rd power. So if we do E to the 3rd to 5 decimal places, what do we get? Good. So 20.0855, and then that's going to round up to a 4. Any questions about that one? And again, it's going to depend on what kind of calculator you're using as to where that E key is located. But as long as you've got at least a scientific calculator, it should have an E key somewhere. Okay, so just make sure you can find it. Let me know if you're having any issues finding it, right, and I'll help you out. All right. Now the next one we want to do 2e to the negative 0.53. So again, we're just going to put that right in the calculator as is. And so what would that give us to 5 decimal places? Good. 1.17721. Any questions about that one? All right, and the last one, e to the 4.8. Again, just put that right in the calculator. What does that give us? Good. 121.51042. That's it. Any questions at all about calculating these in the calculator now? And just make sure in WebAssign, right, pay attention to how many decimal places they ask for, right? Sometimes it'll be 4, sometimes it'll be 6, right? So just always pay attention to how many they're asking for. All right, so now we want to sketch graphs of each of these functions, okay? And we're going to use our properties of transformations to do that. So let's take a look here at the first one. What's the parent function going to be first of all? Let's start with that. So if we want to graph e to the negative x, what would our parent function be? Okay. Can you tell me what type of transformation? So it wouldn't be 2 to the x though, right? Because what's the base going to be? E, right? So it's going to be e to the x. Okay, so our parent function this time is just e to the x. And remember we said that's going to be very similar to 2 to the x and 3 to the x. It's going to be somewhere in between, but it's going to be that J-shaped curve because our base is bigger than 1. It's exponential growth, and it's still going to have a y-intercept of 1, right? So that part doesn't change. We're going to cross right here at 1. We're going to have our horizontal asymptote at 0. It's going to be a J-shaped curve. We're going to have something that looks like this. So that's our graph of e to the x, right? And you could put that in Desmos and see it, right? And you can even compare it to 2 to the x and 3 to the x if you want to, just so you can kind of see how it's between the two. Right, now, if we're looking for e to the negative x, what type of transformation is that going to be? Okay, so what kind of reflection is it going to be this time? Over the y. Good. So this time we have a reflection over the y-axis. All right, so now let's think about that graph then. So if we reflect over the y-axis, where is the y-intercept going to be? Still at 1. Good. So that doesn't change. Where's our horizontal asymptote going to be? Still at y equals 0. But now what type of curve are we going to have? It's L-shaped. Good. So this time it's going to decrease from left to right and approach our asymptote this way instead. Okay, so that reflection over the y-axis now gives us an L-shaped curve. Horizontal asymptote still at 0. Y-intercept still at 1. And let's talk about domain and range. We found the asymptote, right? So let's look for domain and range now. What's the domain of that function going to be? Good. All real numbers, negative infinity to positive infinity. Range is going to be what? Good. Just like e to the x, it's going to be everything greater than 0. So we have that asymptote at 0, and we're looking at everything above. Okay, so that's going to be 0 to infinity. Any questions on the graph or the domain and range for that one? Okay, let's look at the next one. So let's talk about the transformations first, and then we'll think about the graph. So what type of transformations do we have this time? All right, so we have a vertical stretch, I agree. What's the factor of the vertical stretch going to be? 3, good. So the vertical stretch is because we have that 3 on the outside. All right, so that factor of 3 gives us the vertical stretch. What is the 1/2 actually going to do to our graph? All right, it's going to be horizontal because it's with the x. Is it going to be a stretch or a shrink? It's actually a stretch because remember, values between 0 and 1 now, when it's the horizontal, is actually going to give us a stretch because it's always backwards. Right? So this is actually a horizontal stretch. And then when we talk about the factor, what would our factor be? So remember, it's always going to be the reciprocal of whatever's inside there, right? Since we're stretching, we're actually stretching it by a factor of 2. And then if it was a shrink, right, then we'd actually have a 2 in there, and its factor would be 1/2 because we would take the reciprocal of 2 instead. So just remember, as a stretch, it's going to be a factor bigger than 1, right? And if it's a shrink, it's going to be a factor smaller. So it's always the reciprocal of whatever's in there if it's horizontal. Okay. Now, in terms of the graph, right, stretching it horizontally and stretching it vertically, think about what changes here. Where's our asymptote going to be? Still at 0, right? Because if you stretch 0, it doesn't matter, right? It's still going to be y equals 0 as that horizontal asymptote. Where is the y-intercept going to be? It's going to be at 3. Good. So basically, by stretching it vertically by a factor of 3, we multiply the 1 by 3, and that moves that y-intercept up to 3 now. The stretch horizontally isn't going to affect it, right? Because it's at x equals 0. And so stretching it horizontally doesn't move the x value. It only moves the y value when we stretch it vertically. Nothing else has changed here. It's still a J-shaped curve. So we're going to get something that looks like this. So horizontal asymptote at 0, our y-intercept does get stretched vertically to 3 now. But we still have that J-shaped curve. And because we're stretching it vertically and horizontally, it's actually going to look pretty similar to what we started with, because you're stretching in both directions now. All right, let's talk about domain and range. So what's our domain this time? Good. All real numbers again, so negative infinity, positive infinity. And what's our range? Good. Same as before, 0 to infinity. Because again, we have that horizontal asymptote at 0, and then everything's above the x-axis. Any questions on that one now? All right. Example 3. Okay, so we have an infectious disease beginning to spread in a small city of population 10,000. After T days, the number of people who have succumbed to the virus is modeled by the function V of T equals 10,000 over 5 plus 1,245 e to the negative 0.97 T. So little complicated function there, right? Okay, but notice here, V of T just means the number of people that are infected, and then the T here is the amount of time, and that's going to be measured in days, right? So notice here, this is after T days. Now, the first question we want to answer is how many infected people are there initially? And when we say initially, that just means at the start of this spread, right? So at time T equals 0, what is the number of infected people? So how are we going to find that? Good, right? We just plug in 0 for T. So I'm going to say V of 0 equals, we're going to have 10,000 divided by 5 plus 1,245 e to the negative 0.97 times 0. Now, up to you, right? You could put all that right in the calculator as is. Be very careful. Make sure that your denominator is all grouped together. Also, make sure that your exponent on your e is all grouped together to make sure this works out. Or you could go step by step and solve it. If you were to do that here, this one's not too bad, actually. We have 10,000 over 5 plus 1,245. This is going to give us e to what power? E to the 0, right? Well, what's e to the 0 power equal to? 1, right? Anything to the 0 is 1, so we end up with 5 plus 1,245 here. Now we can just add those together in the denominator, then do our division. So we have 10,000 over 1,250 if we add those. And so what is 10,000 divided by 1,250? It's going to give us 8. Good. Okay, now, always think about your units on a real-world problem like this. Okay, so that's 8 what? People. Good. This is the number of people infected. So we have 8 people. Any questions on how we did that one? Okay. All right, so rather than doing 1 day, 2 days, and 5 days, right, that just means that your t value will be 1, 2, and 5. We'll just do one of them. Let's do 5 days just to see what we get. This will give us v of 5 equals 10,000 over 5 plus 1,245 e to the negative 0.97 times 5. And again, if you wanted to do 1 day and 2 days, right, the only thing that changes there is the t value. Everything else stays the same. Okay, but try this now. And again, I'm not going to go through and simplify it just because that's going to be a weird decimal down there in the denominator anyway. So I would put all this in there together, just like with the compound interest problems. Just be very careful again with your grouping to make sure that everything in the denominator is together, everything in that exponent's together. If you do all of that, whenever you get that, let me know what you got. All right, so that's a little high. So let's try this. So let's do the exponent piece. That's 1,245 e to the negative 4.85. So you might want to at least multiply that together just to make sure that that exponent's done first. Okay, good. So if we actually round this off now, right, because we're talking about a number of people, this should give us 678 people now. So I'll give you another minute, okay, in case you didn't get that the first time around. So try it again now. And again, I would just use negative 4.85. That's what I got when I multiplied the negative 0.97 times 5. See if you can get it using that now. Okay, so yeah, so be careful there. Make sure you have that E in there. Okay. Anybody still not able to get 678 now that you've had a chance to try it again? Okay, so I'm going to assume here that people were able to get that. And again, right, if you wanted to do a table of values for 1 and 2, right, you would just change that 5 to a 1 and a 2, right, and you'd get those values for how many people there were. Okay, but just notice here, right, starting with 8 people infected, after just 5 days, less than a week, we're already up to 678 people infected, right? So that's how this exponential growth with a virus actually works. And now, the last piece here is we want to graph this function and describe the behavior. So I'm going to actually put this in Desmos so we can look at it together and then think about some of the key parts of it. All right, so we've got y equals 10,000 over 5 plus 1,245 e to the negative 0.97, and I'm going to use x instead of t here. All right, so we can see right off the bat, right, we have this exponential growth. Now, where would our y-intercept be for this one? It's going to be at 8, right? Because that was our initial population of people that were infected. So I know for sure if I were to zoom out a little bit, right, my y-intercept, I'm going to start at 8 here. And that's really where we want to start the situation in general. We don't care about negative time, right? Because it doesn't really exist in this case. It's really about at time t equals 0, when we start measuring this thing, how many people are infected, that's 8 people. Now, what's going to happen as I continue to go up here? So as my time goes on, right, what's happening to the number of people infected? It increases, right? And it increases at an exponential rate because the more people get infected, the more people there are to infect other people, right? And so this thing's going to grow exponentially. Will it ever stop? When? Say it's going to stop. Yeah, it's eventually going to have to run out of people to infect in general, right? So most people, when they look at this, say, oh, yeah, there's a population of 10,000 people. It's going to hit 10,000. It's going to cap out, right? It can't go beyond that. But watch this. I'm actually going to zoom out. I'm just going to change my y-axis, though. I'm going to go up to 10,000 here. So where does it actually cap out? Where does it stop spreading? At 2,000, right? Why? Why might that happen? In a real world situation, why didn't it infect everybody? Okay. So, but those people are still included in the count, right? Because we're looking at a cumulative amount of people infected, not just people infected at any given moment of time. Okay. So even though people, yes, will recover, they're still included in that tally. So why would it never hit 10,000 people? Think about the current situation we're in right now. Is everybody going to become infected? We hope not, right? So why is that? What could be some reasons why not all 10,000 people in this town actually get the virus? Okay, you could have some natural immunity, right? So maybe you've already had this virus before, right? And you've got some antibodies to it, right? So that's a possibility. What else? Is it possible that in a town of 10,000 people that maybe you just never even come into contact with somebody with the virus? Yeah, right. I mean, that's definitely a possibility, right? Especially, thinking about what we're doing now, a lot of people are staying home more, right? Okay, so it's possible that you just never come into contact with anybody. What else is going on right now in the real world that might prevent everybody in the town from getting it? Vaccines, right? Okay, so it's possible that eventually, at some point in time, they come up with a vaccine for this virus and people get the vaccine, and therefore it doesn't spread to all 10,000 people in the town, right? So that's what we have to think about in situations like this, right? Your natural inclination is, oh, yeah, there's 10,000 people infected, this thing's growing exponentially, all 10,000 people are going to get it. But then when you look at the graph, you're like, well, wait a minute, that didn't happen. And so, what are some of the reasons why that didn't happen, right? Setting it so basically, usually when we see situations like this, we're either modeling them off of past experience, right? So maybe we've had another similar situation in the past, and we know, all right, based on how rapidly this thing spreads and how long it takes to develop vaccines, and how compliant people are with wearing their mask or whatever, right? We know what to expect. These are models. They're not perfect, right? So this might not actually happen, right? It could actually hit 4,000 people. But based off of this model, we would expect that after this certain amount of time, it would max out at 2,000 people in that town, right? But that's what these models are based off of, right? It's just either using what's currently happening, past experience, those types of things to generate a model, and then we hope we're right? So we can predict the future. But we're not always perfect, right? And so same thing with this one, right? It's like, well, we hope that we don't lose a ton of people, but depending on exactly what happens, right? There's a lot of variables going on there. We could, right? And so that's all it is. It's prediction based off of past experience and what's happening currently. Okay. Any questions there? All right. All right. So last thing for this section, continuously compounded interest. So in addition to compounding, monthly, daily, annually, those types of things, we could also compound continuously. Okay. And so if it tells you that you're compounding continuously, this is the formula we're going to use. P is still our principal. E is now the base. R is still the rate, and T is still the time in years. Okay, so all those variables still represent the same things. Notice now we don't have an N value anymore because we're not compounding a certain number of times per year. We're just compounding continuously. Okay, and so a lot of people refer to this as PERT, right? Just so they can remember what the order of everything is. But it's P times E raised to the RT power. Okay? Right, so let's take a look at this one, see if we can get through this. So again, we have an amount of time of 3 years. That's our T value again. We have $1,000 invested. That's going to be our P value again. And our interest rate, again, needs to be a decimal. That's going to be 0.12. Same values that we just saw in the previous section. But now the key word is we're compounding continuously. So that tells us that we're going to use this new formula. So I'm going to say A of T equals P times E to the RT. So now we just substitute everything in there. We're looking for A of T. Our principal is 1,000. E is just E. Our rate is 0.12. And our time is 3. Okay. So go ahead and try that now and see what you get for your A of T if we compound continuously. Good. So $1,433.33. Now, if you remember that last example in the previous section, right? When we did even daily, I gave you that number, we were up to $1,433.24. So you're looking at a difference here of just 9 cents if you were to compound continuously versus daily, right? So it's not going to make a huge difference, right, depending on how much you're compounding, but it does make some over that 3-year period. So this is always going to be the maximum amount of money you could possibly make over a certain time period at a certain interest rate, compared to compounding daily, monthly, annually, whatever. But it's not significantly more than what you would make daily. Okay. Any questions there? All right, so we'll stop there for today. Next week, we'll pick up with 4.3. Again, continue to work on that homework. Let me know if you've got questions. Don't forget your test is due by midnight tomorrow night, so make sure you get that done. And just let me know if you have any questions about that before you take it. Otherwise, have a great weekend, and I will see you all on Monday.